Good morning, Scott here, known as Cantaloupe to some online, and I'm bringing another video to you on a subject that's interesting to me. It might be of interest to you or someone you know, and that is a new way to distribute points geometrically about the surface of a sphere. And that might sound pretty specific, but it is specific, and I do believe it is a new way because I have never seen this approach before, and I'm going to describe it here verbally. And you're seeing me set this up in code on the screen now. So I want to talk about the math in non-mathematical terms, what's happening. And it's a very interesting and elegant idea. And I've been using this approach for a long time, actually, when I need to distribute points evenly, an arbitrary number of points, that is, about the surface of a sphere. So the trick here, the magic, is not having it do the positioning all in one go. So there's a short number of loops that are required to effectively space the points out away from each other, actually, so that you achieve this effect. And this formula can be boiled down to creating the desired effect within, say, 10, 20, or up to 100 or more iterations. And the more iterations you let it go through, the more precise and accurate the spacing becomes. So it becomes a question of quality of spacing that you're looking for using this approach. And the way it works is you take the number of points that you want, whatever number that is. It could be any number from 1 to infinity, and they just cannot be on top of each other. They cannot be at the exact same location. So you start with literally any offset to each other, relative to each other. So you have, say 100 points, they're going to just have to be somewhere not coincidental. Okay, so then the algorithm enters its first loop, and what it does is it takes the first point and then takes the distance from that point to all the other ones in the entire system, and it moves away from each and every one of those in turn by a small amount on a curve. So it's a curve of the distance to those. So what you end up with when you loop through this thing, and you end up with a curve that favors the nearest neighbors, I guess is the way to say it. A curve that favors the nearest neighbors. So it moves away from the farthest ones less because it's moving on a curve function than the nearest ones. And when you loop through this a few times, you get this nice distribution effect. So they're all just trying to move away from all the other ones. And then what you do is, obviously, they end up far away. You pull them back. So each step, they move away on this curve function from each of their neighbors, and then they get pulled back to a predefined radius. And that can be a unit radius or any radius. And then you just repeat. You repeat, and then they space each other out just by nature of the design. And it works really well. So I've gotten this thing down to where it can create a pleasing and practical effect within about 10 to 20 iterations. And that for a number of particles in the range of 1 to, say, 10,000 on modern computer hardware, that's easily doable. That's very practical to perform that spacing in well under, say, a microsecond. But for higher numbers of particles or for more precise spacing, if you're looking for very precise spacing, it could take, a few seconds or minutes or longer, I guess, if you wanted absolutely precise spacing. But this function will also do that too. So depends on how much time and CPU cycles you want to devote to it, but you end up with a very nice effect, and it's evenly distributes all the points about the surface of a sphere. So there you have it. If you have questions or comments, please reach out to whitehotrobot@gmail.com. Thank you.